Hey everybody, Tom Cryptogram here. I just kind of wanted to talk about a math problem I came across recently and decided that I wanted to solve, and I really just want to hop into it. I'll have an entirely different video about the programming side where I have attempted to solve this problem, but for now, let's just jump into the math side and what the problem is, really define what the problem is and kind of what we have. Probably going to see a, yep, so getting to it, the problem is the 3 by 3 magic square of squares. And so if you're familiar with a magic square, or if you're not familiar with magic square rather, it is just a configuration. In this case, I'm only going to be covering the 3 by 3 configuration, where all rows, columns, and diagonals of the 3 by 3 add up to the same number. This is actually fairly easy to do, and they're actually somewhat common. It's one of those kinds of things when you think about it originally, it sounds impossible. You're not going to have three numbers that equal the number three other numbers, but you have one of those numbers that equal that number, and so on. It doesn't really seem to make sense. And then once you see one and start messing with them, it's actually very simple to understand, and it's easier to understand how they work and what the sort of trick is. Big hint: the number in the center is sort of the key and the big trick. Everything sort of revolves around that, even though there are the rows and columns on the outer edges and top and bottom um, also have to add up to that same number and don't use that center value of the 3 by 3. So moving on, here we are, right? The magic square definition we are going to be using and concentrating on, because I don't care about other kinds. There are 4 by 4s and other numbers. There are kinds, and there are sort of sometimes just givings where, well, you can use the same number twice. Like, no, we will not be talking about magic squares where the same number comes up more than once within the 3 by 3 grid. Obviously, the sums will be the same number every time, but within the grid itself, we are not going to talk about negative numbers because we're going to be talking about square values. Negative 7 times negative 7 is 49, just like 7 times 7 is 49, and that goes on to infinity, of course. Uh, 0 actually isn't going to come up much, and we'll talk about why we don't care about it. And then I don't believe there are any other major issues. Yes, so let's talk about the three types of magic squares that I found. Let's talk about the first and most famous common type of magic square you'll find if you look this up and look around. It is called the Loshu. I hope I'm not pronouncing that too badly. I believe it is the Loshu square. It was discovered in like 2200 BC in China, and that's sort of the earliest known recording of it. And it is this square that we see in the upper right hand corner. This is a real magic square that uses the numbers 1 through 9. And all of the rows, columns, and diagonals add up to 15. Very interesting and really kind of cool. The Loshu, we're going to call it the sort of common type because it's the common type you're going to find as you go looking at and looking for magic squares, but it's also the most common type that we can calculate, and we'll go over that a little bit later. Uh, so you can see pretty quickly that we have this number 1 through 9, and so we have this sort of configuration of our values. And if we just add 1 to each one, or add 17 to each one, or any number to every one of these, we are simply going to translate that value in that sum to, to the right on the number line, to a larger number, right? If we add 1 to each one, instead of getting 15, we're going to get 18 because we have three numbers that are getting, for each sum that are, scaling up by 1, translating by 1, actually. So translation, if you're not familiar with rendering and gaming and different things, that's just when you move something. So we can rotate, translate, which is move, and then scale things up, right? And scaling, I think, is pretty obvious. Rotation's pretty obvious. I think translation, meaning moving, is a little maybe unusual. We can see in the Loshu square the ratio between all adjacent values is a constant. So the ratio between 1 and 2, right? There's this like distance of 1 in this case. But if we were to scale the Loshu, if we think about it for a moment, if we multiply every number by 10, and we've like in the upper left going down 4, 3, 8, we would instead have 40, 30, 80, and that would add up to 150, right? And all we've done, I think, right? And yeah, so we've scaled it up where they still add up to 15 plus a zero on the end. So interesting. But this scaling and this difference between the lowest value and the next lowest value is now 10 rather than 1, right? So that's how the scaling works. Um, so we can translate it, we can scale it, and then we can scale and translate it or translate it and scale it. It doesn't really matter. The last thing to mention, we won't be going over this a ton, but when we have the Loshu square, we can sort of rotate the outer um, numbers or mirror them and do whatever we want with them. But when we talk about a formula later on and how we sort of generate these Loshu squares, generate all the magic squares and things, we're always going to try and search for this orientation where the bottom center value is the lowest value and the top center value is the highest. And then we'll talk about where the numbers kind of change from there. I believe actually 2 and 8 always stay where they are. I use a mirrored version of this, so the 2 and the 8 are flip flopped, if I'm not mistaken. We'll talk about it a little bit later. But just so you know, that is coming. So we have our examples at the bottom where we've translated 1 just by adding 100 to everything, and we've scaled by 1 by multiplying by 10, right? So then we have another. Oh, my bad. I moved this stuff around real quick so that you can actually see what the heck I'm talking about and get maybe a better idea of the translated and scaled. And moving on. So the next type we're going to talk about is the near Loshu. The next type we're going to talk about is the near Loshu, and as you can see in the bottom right hand corner, it is like the Loshu where the middle values are in the same spot as the so like essentially if we looked at the smallest value, the highest value, the 1 and the 9 would be in the same spot, the second highest and third highest would be in the same spot, and so on. So it still has this same configuration as the Loshu, but this ratio is gone. The ratio of a normal Loshu, like we talked about, right, is this distance between the lowest and then the second lowest, either being 1 or 10 in the case of the scaled one, 1 in the case of the normal Loshu, and so forth. This is gone in this case. We can see very quickly that going bottom left to upper right, these middle values 4, 5, and 6 are only 1 away from our center value. But all of the other values are 499 and 501, and then in between the center value, or from each other, and from the center value. So our ratio is completely blown away. This is an extreme case. When we get to the formula in a minute, what I started with is the number 1000, and then took the numbers 1 and I think 500 or 501, I guess 500 or something like that, right? And then did my did my formula from there, which makes these these two values just extremely far apart, and then puts these middle values adjacent in this case to the center value. So I'm kind of getting ahead of myself, so don't worry about that too much. I just think it's smart to mention where this is coming from and what's happening. You won't always end up with these just being 2 away, one away each, or whatever from the center value, and then these massive differences all over the place. They can be a lot closer, and they will actually converge on to being a Loshu square in a certain way and having that ratio. And so let's keep going. And then the last, that's really the third type that I am aware of and have been able to generate and understand, and all of these, is I'm going to call the Haishu. C-Line, which is the programming thing that I use instead of Visual Studio, actually generated this name. I was going to name it something different based off of the first person that I was aware of that showed off the formula that we're going to talk about in a moment. And then when I typed in Loshu, hit space, like comma space to make another variable, it had Haishu already named for me, and I could just hit tab and use it. And so now it's called the Haishu. I hope to God that is not some sort of weird Chinese slur or something, and we're going to go with it, but it's a bit of a nail biter sometimes when you do stuff like this. So Right, this is still a magic square, but the third, fourth, sixth, and seventh values are not in the same place on the square. So I believe the third and fourth values actually go across, right, the center here. The third and, I'm sorry, the fourth and sixth values, right? So these two values that are the closest to the center value, right? And they're just a little bit outside. In this case, again, because I use some extreme values and some little trickery and things to try and make it very obvious, we can see 4, 5, and 6. 5 is always going to be our center value of 1,000 in most of the examples I give. Again, it doesn't have to be. It's just a nice number I picked that is easy to work with and gives me a lot of values to sort of move around. 4, 5, and 6 go from right to left across the center rather than being the upper right and lower left diagonals. And so we have a completely different type of magic square that simply doesn't fit the ratios of the original magic square. It doesn't fit the configuration of the original magic square, but everything still adds up to 3x. That's it. I don't know what else to say about that one. I did do the math by hand on this, so I'm really hoping I didn't mess up somewhere. Right, it seems to me that this is one less than 1,000, this is one less than 1,050, and then if we add, put those in from this 2 here, we've got 950 plus 1,000 plus 1,050, so we end up with 3,000, and that's it. So, right, yes. I keep second guessing myself even though I've done the math so many times, but I haven't used the calculator for a lot of these. But I did use my computer program to generate a bunch of different things, and it's doing the math and checking for me, so I can do these. Yeah, I can have it do these quick generations. So I'm pretty confident. And if that ends up being off somewhere, it's because I did the math wrong by hand, not because of anything else. I promise these other configurations exist. So. Right, so we've kind of gone over the meat and potatoes here. 3, 4, 6, and 7 sort of swap a little bit where they belong, and in these two vertical columns that they exist in, it's going to be these bottom left and upper right pair that sit here, and we have actually this Z shape stays constant. In the way that we configure our values by putting the highest and lowest in the top center, bottom center, and then working our way out. The fourth type. I do not believe there is actually a fourth type of low-shoe square, but I've tried very hard, or magic square, I'm sorry. I've tried very hard to generate one. The only way I can see it working is when you think about the magic square and how it's configured and how the numbers relate to each other. There is a relationship, and what I've kind of written here is that like every corner, when you're doing a magic square, can see every other corner and is eventually added with every other corner. In picking the bottom left here and working our way out, right, the bottom left is going to add with the top left as a column, the bottom right as a row, and the top right, its opposite corner, as a diagonal. Happens every time. And this is really why all of the magic squares always need the center number to be the number in the center of the 3x3 grid to be the middle value that everything sort of pivots around, which we'll talk about more in just a moment. And there's really no way around that I've found. I tried and tried and tried. Looking at this X that we have here in this bottom left configuration, it can't see and is never added with the other two X's. So I tried to find some way, some strange configuration, but the thing is, they do have a relationship with this X here, where this X, when it adds with the center, has to create another value that adds with the original X, our corner X that we're talking about. And the same for the other X that it can't see on the right-hand side. Has to generate a value coming from across the center. So I try to figure out a way where center could be 0, either the lowest number in the entire list or the highest number in the entire list. And so we have these smaller values that pivot around it, but those never work out. If you have it as the highest value in the center, the the values on the edges that don't add with the center right, the rows and the columns that are on the extremes, somehow still have to add to 3x. They're or not 3 times the center. It's not or something. It's very strange, and so I've tried over and over. I feel like it could work, and I just haven't thought about it enough and tried enough. But I did try sort of coming from the extremes, and I do think that if this would exist, that the center value would have to be either the highest or lowest value. It'd have to have some sort of extreme relationship, right? It has the extreme relationship of being definitely in the very center of all values already through all of our other magic square types, but that's kind of it. I'm going to move on for now, but I'm always looking for a counterexample of any kind that then I can work with and then understand how those ratios might work. Since we have these different types of magic squares, is there a test that sort of works with all of them? If I have, no matter what values I have, if I suspect that all 9 values or some number of, a finite list of numbers, hopefully that I can quickly do by hand and mess with, is a magic square, how would I determine that some of those values can create a magic square? And so, right, in my example here, I say if I gave you 9 numbers and said it constructs a magic square, what steps would you take? You would put the numbers in order, going in ascending or descending, it doesn't really matter, so that you can work with them. Take the middle value, put it in the center. Take the highest and lowest values and put them in the top, the highest being in the top center and the lowest being in the bottom center. And then we can guarantee that the bottom right value should be the, let me double check my notes here before I misspeak. The bottom right and the upper left would be the second highest in the upper left, so one value above our bottom center. And then our 8th highest, one value below our top center, would go in the upper left and lower right, 2 and 8. And then from there we could determine very quickly if there is another number that adds with our either sort of bottom left 2 values, or our bottom right 2 values, or our top left 2 values, to create 3x, 3 times the center value. Because we know in all of our configurations, all of the time, no matter what, every single row, column, and diagonal will be 3 times the center. I don't know that I mentioned that before, but I feel like it's a key. So the low shoe, near low shoe, and high shoe all do this all the time. The center value times 3 is what the sum of any row, column, or diagonal needs to be for it to be a magic square. So that's kind of it. So the unknowns that we have are values 3, 4, 6, and 7. We don't know what configuration they're going to be in to create our magic square. So moving on, generating each type. How do we generate each of these types? So we know there are magic squares. We know we can start with some value. We know how to test for them, and so on. So how do we generate them? And how have I generated these values and tested with them and checked all of my stuff so far, right? And it's fairly simple. So if you want to generate a magic square, you can pick any value that is, I think, greater than 10. If we're going with positive integers, and then you pick an A and a B, where, right, A and B are 2 different values, and they do not add up to our center value. They must be less than or equal to the center value. If they are equal to the center value, we'll get a 0. Let's talk about that in a moment. And so of these 2 values that we pick, I've obviously been picking 1,000 quite a bit, and then just picking any random numbers that add up to less than 1,000. I'll put 1,000 in the center. I'll label the smaller of the 2 values, because they can't be equal, as A, and the larger as B. And then we'll look at the formula in just a moment. And it'll maybe be a lot simpler And then, right, I have a note here, b can't be equal to a, or we will get multiple sets of the same value in our squares or in our cells. And right, and then we'll talk about square values in just a moment. So let's just look at the formula. I'm actually going to jump ahead one little bit. And this is what our formula ends up being, right? So we have our a and our b that we picked. Our high value will end up being x plus a plus b, and our low value be x minus a minus b. And hopefully this starts to make a lot of sense as to exactly what we're doing. So if we add a plus a here and a plus b here, this is why this ends up being minus a minus b. And then we just go for opposite corners, right? If we did plus a here, opposite corners minus a, plus b here, opposite corners minus b, and then these are sort of the in-betweens. This is where it's kind of interesting, is that you would expect these sort of in-betweens to make the like 4, 5, 6 in between all of the time. That's just not how the math ends up, because of the relationship of the size of a and b. And so that's kind of it. And so every number in any of these magic squares that we ever look at, the right 4 and the 6 that are closest to our center value 5 are going to be the same distance apart from 5, either 1 apart or 2 apart or 3 apart. And this is where it's sort of interesting that not all of the values though share that ratio that we talked about. They are not all one distance apart from the lowest number to the next, and so on. They can have these like disparate values to them that are very far off, and so the sort of number line area that our magic squares cover can vary greatly. And so now that we know how to generate a magic square, we know that we're either going to get a low shoe, near low shoe, or a high shoe, right? Those 3 types. And so I have figured out what it is that makes them become those types, right? For a low shoe and a near low shoe, I actually can't remember off the top of my head what it is. They need to be some particular distance apart, and now I can't remember what it is. Oh well. Maybe some other time, or maybe I'll figure it out and have an injection into this video here that talks about it. But the real thing that we want to know, in my opinion, is what makes it a low shoe or a high shoe, or when is it a high shoe or not. And it is a high shoe when A is greater than 1/2 of B. And this is where the numbers suddenly flip when we do our orientation and our formula that we've covered. And again, we know that A plus B is less than or equal to the center value, so that's already a restriction. And so, right, the first thing I did when I was kind of looking for these was make A and B 1 and 3. Can't be 2 because B can't be 2A, so I made them 1 and 3, and then just added them up, added +1 to them all the way up until A plus B was 500, I'm sorry, 1,000. And so at 1,000 you end up with a 0, I think, in the far left center. But until then, they were all these, except for the very first set, I think, 1 and 3, all of them were these high shoe types. And then I sent A, I did minus minus A, or I set B up to 1,000, and then just did minus minus A. I don't know, something like that. Basically, I sort of, instead of having them follow in tandem all the way up until this max value, right, which is what I did originally, then I set A to 1 and B to 999, and then just had it run all the way down to back to 3, essentially, and then counted. And all of those values from 999 as it came down towards 1 were all just normal low shoe or near low shoe values, or squares rather. And so it had everything to do with A being closer to B, and within that ratio. And yeah, so if you kind of mess around with it, it's maybe easier to understand. It's very hard for me to like show visually because I don't have any video editing or math skills like that for a YouTube video. And so that's kind of it. So what is left? Yeah, so we can see pretty easily that all values are these sort of matching pairs, and they match where their distance from the center value is the same. They are equidistant from the center, right? Um, because we need these two values plus the center to equal 3 times the center. And then so we sort of end up with, when we do have those rows and columns that are on those edges, that don't go across the center, we still end up with this ratio based off of the center, and then adding and subtracting values that will sort of cancel out. They just cancel out a and b, and so we end up with really just x plus or center plus center plus center. It's hard. I call it the x all of the time in my variables and different things. So x and center are kind of the same thing. I'm trying to steer away from that in this video. And so really that's it. You end up with 3x all of the time, no matter what. And that's it. This is every configuration we're able to make. So we finally got to the square numbers portion of the entire thing, and this is where I'm kind of done. I don't really know much about square numbers and their values. I've only found a couple of things that I don't already know. I don't look at square numbers much. I'm not a mathematician or anything like that, so I don't have any of this prerequisite knowledge or anything. I just kind of had to mess around with the numbers and figure out what's what. So if we want to find a magic square of squares with the constraints that we've already discussed, unique values, I guess that's it, and then there's square values. We don't have, we have much fewer options all of a sudden. We can't use 0. 0 will never come up because 0 would imply that somewhere we do cross the center, no matter what section you have in the square, right? Even though the top row, when you add it up, it didn't cross the center, each of those different cells within the 3x3 need to add up with something else eventually that crosses the center. And so when it crosses the center, if you have a 0, then the other number has to be 2 times the center. Well, if the center is a square, you cannot have another square value that is double another square value. You can't have a square value that's double another square value. That will never happen. They are always off by at least 1 or -1, depending on how you're kind of looking at it. They're off by 1 as the absolute value of that difference. And that's because they essentially are based off of odd numbers. The difference between 2 squared and 3 squared is it 5? Yeah, 5. And so the difference between 3 squared and 4 squared is going to be 7. And the next one's going to be 9, and 11, and 13. And it's just essentially every time you want to get the next square value, if you're not going to just multiply the square roots essentially of the next numbers, you can just add 2 to the previous value, which is an odd number, and then add that to our current number, essentially. Or to put it in a more clear way that isn't stupid, just keep adding the next odd value to our value, and we will generate all of the square values. That is a completely different way to do it, and but exactly the same in every way. So because of that, these odd values are never double each other, because if you double an odd number, you're going to get an even number, sorry. And so you can't have this even difference between square values. It has to be an odd. The difference between 2 square values is going to be odd. So using that kind of knowledge, we can get rid of a few things, and then I have essentially just created a brute force program that looks at a square value, looks towards the extremes, right, where I know that once we're going to cross double our index, I don't care anymore, I don't have to test, and so I just sort of keep increasing these square values by 2 and then going up.